Let me define this. The cell graph of a grid class is formed by, I'm going to connect cells in the same row or column unless they're separated by another cell. So connecting non-empty cells in the same row and column if they aren't separated. An example is probably best. I'll just do dots where we have things. So these are the non-empty cells. There are, so the cell graph would go, these are connected, these are connected, these are connected, and that. Notice that that's not an edge because they're separated by something in between. So that's this graph, and then the theorem says that a monotone grid class has an infinite anti-chain if and only if its cell graph has a cycle. So this one that I've just drawn, if you replace the dots by AV12 or AV21, that has an infinite anti-chain because you can cycle over. So the ones that don't have an infinite anti-chain are precisely the forests. So that makes you suspect that the forests are the nice ones, and maybe we should start by trying to count the forests. So motivated by the idea of counting the forest, we came up with another version of grid classes. So these are geometric. Implicitly, they're all monotone grid classes. And this is really the new research that I'm going to talk about today, are about these geometric grid classes. So the idea is quite a bit different from the way it was framed over there. First, we draw a grid, and we connect, well, for some of the cells, we connect opposite corners. So for instance, if we were looking at like actually trying to build an X, what would we do? Well, we'd take a 2x2 grid, and then we connect that corner, that corner, that corner, that corner, and that. Or if we wanted to do our sort of two increases next to each other, and of course, there's nothing stopping us from leaving a cell in. Now, we choose points on this picture. We choose a finite number of points on this picture. Now, if I take a finite number of points, I can number them, and if they don't share x and y coordinates, I can number them by their height. So I'm just going up, writing down what they are. 1 through 6, reading bottom to top. And then I can read them off left to right. So this would be 6, then we'd hit 2 first, then 4, then we'd hit 3, then 5, and then 1. So it makes sense to say that if we have a finite number of points that don't share an x or y coordinate, they're order isomorphic to a unique permutation. So we choose a finite number of points in this picture. They are order isomorphic to a permutation. And our geometric grid class is the set of permutations. So these are the classes we're interested in. They come from these pictures. So first, let's look at this thing. How does this relate? So this geometric class I'm going to draw like this versus the grid class that we had over there, that's sort of the corresponding grid class. So how do those relate? Well, let's take something on, we know what the ones on the left look like as a picture. Let's take one on the right. So we take a permutation that looks like this. So what a permutation can be described as a square. It's got some divider. It's got some increasing set of points here. And then another increasing set here. Okay. Now I can connect the points on the left with lines. And the ones on the right. Lines. And the point is, by stretching and shrinking this, I can make this a straight line. Right, by stretching and shrinking this, I can make this one a straight line. I never have to touch this one, actually. So I can straighten this out to get it into that form. So actually, these are the same exact classes. Okay. And more general, if you think about it, if you have, it comes down to exactly the cell graph. If you don't have a cycle, then you can go from one cell to another fixing it to make it a straight line. And you'll never come back around yourself. But if you do have a cycle, then you have a problem. So let's look at this thing. Let's look at this x. So its corresponding class over there would be no increase, no decrease, no decrease, no increase. Well, just looking at the basis for the grid class that we have there, skew merge permutations, it's 2, 1, 4, 3, 3, 4, 1, 2. So one of the permutations that is in that class is 2, 4, 1, 3. Well, how could I draw 2, 4, 1, 3 on an x? Let's think about this. I'm going to try and draw it on an x. Well, I'll just draw it. 2, 4, 1, 3 would look like 2, 4, 1, 3. The first question is, where are the dividing lines going to go? Well, with a little bit of playing around, you can see that you're going to have to break the points up, so there's one in each cell. Okay. So just believe me on that they have to be broken up. Now, could they be drawn on these lines? Well, let's look about it. This 4 is above the 2. Now, if I had the 4 here on this line and I went over, anything lower than it is closer to the origin. So, sorry, this is 3. Oh, numbers we can talk about. So the 3 is closer to the origin than the 4. The 3 is somewhere down here. Now, when I go down, the 1 to the left of the 3, that's closer to the origin than the 3. And now I go to the left. Right, the 2 is above the 1. Everything that's above the 1 is is closer to the origin than the 1. So the 2 is closer than the 1, which is closer than the 3, which is closer than the 4. This is a contradiction. Okay, because the 2 actually has to be further away than the 4, which you can see just reading down. So whenever you have a cycle, you have a permutation like this that's not in the geometric grid class. So these are not the same thing, except that when you have a forest, and that's exactly where Max Murphy and I's theorem applied, then they are exactly the same. So this was the first hint that maybe it's not the forests we need to look at, but maybe it's these monotone grid, these geometric grid classes. So now let me give you the theorems. These are joint with Albert, Atkinson, Bouvel, Ruskuc, and myself.
Is that a law firm?
Okay, so here are the theorems. Geometric grid classes. Okay, the first thing is that, well, we knew that the forests, the monotone grid classes, if they were a forest, they didn't have an infinite anti-chain. That carries over to the geometric ones. No infinite anti-chain. Okay. They have finite, and more impressively, I think, computable bases. I mean, not that we actually have a program to do that, but one could imagine one writing a program to do that. Sort of spell out in the paper. And probably the nicest of all these results is this one. So it's the hardest. They have rational generating.
So they're all trivial. Everything external is trivial.
Yeah, thanks. It takes a long time to do these things.
It's not trivial before we trivial.
So yeah, they're the nicest permutation classes there are. They belong to the family of the nicest ones that there are. Let's see. Where are we at?
But did you characterize what's rational in your previous work?
No one's ever going to characterize all the rational classes.
Oh, you gave a large family. There's known to be rational.
Yeah.
So this does not overlap with the previous one.
Oh, no, there is some overlap.
Yeah, but it's not the same.
Right.
Nothing. It doesn't do it.
So all these proofs have the same tool, and that's that we encode these things with words, like we did over there. So when we did, like we did on the board I just erased. So the idea is that we encode by words. And basically, once you encode these things by words, you get the no infinite anti-chain for free. And then once you have the words, you start thinking about a rational generating function. So if these words turn out to be a regular language, and if you can characterize permutations by a regular language of words, then you have your rational generating function. And that's how the proof goes. So I'm going to give you two examples, or three examples actually. Let's go back to this thing. When we first counted these things, we said, well, we're going to read from bottom to top, and we're going to write down letters when we see an entry. So we have A's and B's. We're reading from bottom to top. And what I want to point out here, we didn't need this observation, but really that means we're reading this cell from left to right, and this cell from left to right, right? Because as we go along this line, up, we go right. Okay, so really, we have a starting corner down here, and we're reading up to the ending corner. And basically, we're recording an A or a B based on how far away the points we read are from their starting corners. Right? So if this thing is point 2, and this thing is only 0.1 from its starting corner, we record a B and then we record an A. We're just sorting the points by their distance from their starting corners. Okay, if we go to the X, and then remember we had to take care of things with multiple representations. We go to the X. What are we doing? Well, one way to encode this would be to read this. I'll read this top row, top to bottom. That means I'm going to read, we're going to go down this way. So this first column goes left to right. And that means that this thing is going that way, so it's going bottom to top. We come along here, this is going top to bottom, so it's that way. That's that. And that means this is going this way. And there we have that arrow. So everything was consistent. And again, we have starting points. I did it based on the outside. You could also start at the inside and work your way out. And we just work our way in, recording a letter, A, B, C, or D, and that encodes the permutation. We need to worry about things with multiple encodings, but that's the bulk of the proof, actually, is multiple encodings. Okay, so you should be a little bit skeptical. What would we do instead of these two carefully constructed examples? So you might say, well, let's just read this one bottom to the top. It's going that way, they'll read that way. Come down here, that's bottom to top. If we go over here, that's bottom to top, it's going that way. And now, this says we need to go that way. But this says we need to go that way. We have a problem. This is my favorite trivial part of the proof. There's an easy way to fix this problem. Cut everything in half. So now I've cut everything in half. And now it all works. Right? So it's a bigger grid class, but everything that was in my old grid class could be drawn on these lines. So of course, if I subdivide the lines, they're still drawn. And if you can be drawn on these lines, then ignore the middle sections, you can be drawn on the old lines. The lines haven't changed at all. And now, you can check that it all works. This goes that way, this goes that way, this goes that way, and etc. And essentially what we've done is we've replaced either of these two. Goes to something like an X. Well, it goes to a certain subsection of an X, and we already knew how to do the X. And if you tile a bunch of X's together, just tile this together, these arrows together. Okay. So that's the encoding, and then the basic idea of the proof is figuring out, which takes 20 or 30 pages, how to make a unique encoding for permutations, because these things can jump around. Part of it could be over here, and then it could jump over there, and another encoding. So I will stop there.
Thank you very much. Vince, it would be great to answer questions in private right now, but also we're going to take Vince out for dinner at 6:45 at the usual place, Evelyn's Restaurant on Eastern Avenue. If you'd like to join us, and this includes Professor G and anybody else, please let me know immediately. If you don't like to join us, just run away. Thank you. Okay, come.